What's going on, guys? Welcome back to this video. Today we're going to talk about the Vanhelsing ransomware. Does that name ring a bell? The Van Helsing is a name of a TV show that aired on Netflix. It is a vampire TV show. It was entertaining. I watched it. I recommended to watch it. Now the thing about this ransomware is that supposedly the name of this ransomware was inspired by the TV show. I haven't found a proof to this fact yet. But anyway, it is a Van Helsing ransomware. It was released or it was debuted in March, on March 2025, this month. It was seen in the underground forums, and it's advertising itself as a ransomware as a service. So basically, this means that anyone, even if the person is not a hacker or a cybersecurity, any user can download the ransomware, have access to its control panel, and then send it to the victims. That's why it's called the ransomware as a service. The ransomware employs the double extortion method. So basically, it first asks the user to pay the ransom. Now, if the user does not pay the ransom, it's going to leak the data of the user. So, if the ransomware infects the machine with sensitive files, these files will be leaked seriously to the public if the person does not pay $500,000 as stated by one of the victims. Now, the other thing about this ransomware is that it has a control panel where the user or the person who purchased the ransomware can access the control panel, download the ransomware, and send it somehow to the victims. In this video, we're going to analyze this ransomware using two methods: an online sandbox, which is hybrid analysis, and then we're going to use Ghidra to reverse engineer the ransomware. Let's get started. Okay, now we start the analysis process. So here in hybrid analysis, we can submit the file by clicking on, by dragging the file and dropping it here, or by just clicking on drag and drop on this area, select the file, and then put in your email, agree to the terms, and then select the operating system. In my case, I selected Windows 10. You can select Linux, you can select Mac, or you can just use a quick scan. Then click on Generate Public Report. Now, after doing so, here are the results, and we can see that it was flagged as malicious immediately with high confidence. Here are the reports by Antiviruses and reports from Falcon Sandbox. Okay, first we have antivirus results. CrowdStrike Falcon has flagged this as malicious, and also Meta Defender. You can click on more details to have a look at what are the AVs or the security solutions that have flagged this sample. Cyber Defender, Avira, most of them have actually flagged the sample, except we can see the ransomware slipped through McAfee, and has slipped as well from Komodo Clam AV as well. So these are the, okay. Next we have the Sandbox reports. This is where the analysis comes. In the analysis report, we can see that the file or the ransomware was flagged as malicious with 100% threat score. Now, information relevant to this analysis can be seen if we scroll all the way down. Here are the static analysis details. Among them is the hash. This can be used and looked up in VirusTotal. So in VirusTotal, here we can use the hash, and we can see other information as well. Here it is flagged by 53 security solutions, and that's actually a quick response date to this ransomware, given that it has been spotted this month. Going back to the analysis here, here we can see the format, executable, exportable, executable, and the imports. Scrolling down, we can see the metadata. These are actually relevant to the analysis if you don't want to open the file dynamically. The file sections. Now here what I found in the interesting strings here, I found this one. This represents the Van Helsing encrypted file structure. So it starts with the key. Now this one is the same key, but in hexadecimal format. This is the end of the key. Then we have the nonce, and then the hexadecimal representation of the nonce, end nonce, and these are the encrypted chunks. This one and this one and this one. All of these can be brought all together to represent the encrypted chunks. This is the note, right? That's first seen when you open the ransomware. No news is good news. Your network has been breached, and all your files, personal data, financial reports, and important documents has been stolen. So these are the strings that I have noticed. This is the README file. If we scroll up, take a look at the file imports. Usually we pay attention to file imports used by the sample because we want to build a pattern of what are the common file imports used by malicious samples. Now you can see imports that indicate manipulation of the registry keys. If you click on the kernel DLL, we can see create file, close handle, And these are actually used by the ransomware to create the encrypted files and to close the handle on the non-encrypted files. Net API, shell, command line to arguments. And this is because the ransomware operates in two modes, the silent and normal mode. So when the attacker executes the ransomware, they choose whether to execute it in silent mode or in normal mode. And they need to specify so using command line arguments. That's why this is used here. User DLL, that's the message box. Close socket, connect, free address, get address. We will see all of these when we analyze the sample using Ghidra. But these used to perform a network activity. For example, get address info to resolve the host name into IPv4 address. So probably the ransomware performs some sort of network scanning and host discovery. We're gonna verify this when we analyze or when we reverse engineer the sample using Ghidra. Extracted files section. These are the files that are unpacked when the malware is executed. First, we see the README file, and that's the ransom note. And then we have this file, which is non-ISO extended ASCII text. Okay. Next, we have two other files, which are they look to be text, but the runtime process is the same process that executes the malware. Okay, we click on the screenshots. Okay, the screenshots are not clear here, right? The ransomware does not perform any, as you can see in the network analysis section, we don't see any network activity because the ransomware does not contact the C2 unless the ransom is not paid. So when the victim refuses to pay the ransom, the files then are exfiltrated. But this doesn't happen immediately. That's why the network activity or the network analysis is not doesn't show any activity here. And that's because this is a second stage in the ransomware's inner workings. And here, this is the note. Okay, we analyze this. All right, now next we're gonna move on to the reverse engineering with Ghidra. Okay, so in Ghidra, let's now start with the main function. So in the main function, we start with initializing CRT. So here we initialize or we set up the C runtime. The ransomware sets up the C runtime. If it fails, it's going to call a fast fade routine, terminating the process. Then we have a startup lock here. So here the function acquires a startup lock via this call, and then it checks a global flag represented by this to determine if maybe static initialization has already been performed. If it wasn't initialized, we see the flag is set to 1, okay, and then it calls the interim to execute error returning static constructors. If any of these return a non-zero value, okay, the function aborts the initialization. Basically, it restores the exception list and returns an error code. This one. All right, let's see. And here we have another call to initialize term to run the standard static constructors, those that do not return error codes. The flag is initially set to 2 here, indicating that the initialization is complete. Okay. Now we're just trying to dissect the code here. Let's see what are other important parts. Okay. Now we have this. We have a call to get wide win main command line. So here it is called to obtain the startup parameters. I mean, like how the window should be shown and the command line arguments. It was believed that the ransomware runs in two modes, normal and silent mode. We're gonna see how this works. And we see a call to this function. Now let's have a look at this function here. Okay, so here we see the main application logic. All right, so in this function, we have several function calls. We have a function call to this function, and we have a function call to that function. So these functions used to verify that the environment is set. I'm not going to check them. And then we have a mutex creation by using create a mutex here. So basically, here, if the flag here that's used is this one, okay, referenced here. And if this flag is not set, the code is going to create this mutex. And here we can see the name of the ransomware Vanhelsing. And then it performs a check on the mutex itself. If the mutex already exists, okay, hence indicated by the error code here in hexadecimal, this means that the mutex already exists. If it does, it's going to go to abort the execution. This is a common way to prevent more than one instance of the program from running simultaneously. Okay, let's have a look here. What do we have else? And then we have a memory allocation here. A large memory block is allocated with this size and is stored in a global variable. And then we see several fields within this block are initialized to 0 here. Okay, let's see here. And we can see here, additional initialization is performed by calling the ordinal 115, by passing here, as you can see, numeric parameter and a local buffer, and by allocating a small memory block. Okay. And then we have this helper function is used to fill a 32 byte buffer with the data. And the parameters here suggest that it might be setting up some configuration or key. This is probably the encryption. Okay, have a look at this function. Okay, we're going to get back to this later when we talk about the encryption routine. And now we have drivers being set up here. Okay. So this function sets up the environment and the necessary drivers and threads for the ransomware to work. Okay, so now the next step is to locate the code blocks responsible for the encryption process. After we have explored the main function, the functions responsible for setting the environment and the processes, now it's time to look for the code blocks responsible for the encryption. So one of the popular methods is to use the search. So by using the search, we can locate specific strings within the program that would allow us to locate the code blocks responsible for the encryption instead of sifting through all of these functions one by one. Now, usually ransomwares use Windows API calls. Now, if you have checked the past video, I analyzed the Ryzen ransomware, where we located the code blocks responsible for the encryption by using the native API calls or the crypto API calls, because they are usually used by ransomwares to perform the encryption. Now, this time what worked for me is by using plain strings. Okay, so if we search for the keyword encryption and we select all fields, search all, you can see how we have hits here. Here we have a statement saying error opening file for encryption. So probably here we have located the code block responsible for the encryption. Still, we have to take a look. So this is the function. The function ends with 370. Can I double click on this function to open it? And this is the function. Let's have a look here. Okay. So what do we have? First, here we have variable declarations. All right. And then let's see here. Some initializations. We're gonna have to skip these. Okay, here you have a function call. So this function, and we have this function as well, and we have this function here. Probably here are used to complete the construction of the stream objects. These are stream objects, so these functions are used to complete the construction of these objects. Basic iStream is a stream object. These functions likely correspond to constructor routines or setup routines for the C++ library. We can skip this for now. We are interested in locating the encryption block here. Okay, so next we have a call to this function. So here the function calls the highlighted function here with the file buffer object. The file parameter, or parameter here is the represents the file name probably, and a mode value here, represented in hexadecimal. This mode is likely specifies that the file should be opened in binary mode. Okay, so here we open the file for the encryption. Probably here is the ransomware preparing files for the encryption. Okay, next, let's see here. And next we have, can I skip these for now? Okay, error handling. And next we have a call to this function here. So after the file is opened successfully, okay, we have a call to this routine that likely performs additional stream operations. Okay, we're gonna skip this one. And next we have a call to this function here. The function here is called probably to return the size of the file, okay, or the amount of data available for encryption. Now, in some cases, it further queries the file using maybe a function pointer call with a specific offset. In our example here, the offset is this one. This is the offset. Okay. So after all this finishes, preparing the file and opening it, allocating the right memory size, we see a call to these two functions. These two functions are used to prepare for the encryption process, the key generation and the nonce generation. So basically, the function here invokes the routines, this one and this one, to populate the local buffers, local 50 and local 30. So these are the cryptographic key material and an initialization vector, or what's called as the nonce. Okay, next we have a call to this one. Now we're gonna have to look for the buffer allocation. Here, the buffer allocation happens through the variable local 89C. This is the output buffer is allocated with a size slightly higher than the input. The size here is UVR9, if you remember. Okay, UVR9 plus this value in hexadecimal. That's an adjustment if the file is very large. This buffer is intended basically to hold the encrypted data. So the encrypted data is held into the local 89C. All right. Okay, let's see. Okay, after we finish here, the loop is finished, we have a call to this function. So here, the function have the argument, the parameters here, local 89C, that we talked about earlier, holds the encrypted data or the encrypted payload, PVR4, VAR7, local 30 and 50 for the cryptographic key and the nonce. So basically that's the function responsible for the encryption routine here. So it takes as parameters the output buffer, the input data buffer, the data length, the nonce buffers. Now we see subsequent calls to these functions, okay, to convert the row key and nonce into formatted representations, the appropriate representation. Then here, through these lines, the code sets another set of stream objects, this time for the output. Now, the very important observation here is this line. Existing file name equal to local 8AC. Here, it reuses the original file name, okay, represented by local 8AC to open the file for writing, this time in a mode specified by the hexadecimal value here, this one, which could actually indicate binary output with truncation or creation of a new file. Okay, then we see writing of metadata or encrypted data. Let's scroll down and let me show you here. So it starts with here, this line. So here, the function writes a series of markers and data. So it writes a header string, this one, followed by the formatted encryption key here. It does the same again for the nonce. And also we have end nonce here. Finally, okay, scrolling down, it writes the encrypted data here from the local 89C we saw earlier to the final file. And lastly, here we have a call to this function. So here it finalizes the output stream. If we scroll down again, we can see calls to these two functions. So basically using these two calls, the function renames the original file by appending the extension vanlocker. That's the extension used by the ransomware. This renaming is a common tactic, by ransomware. So basically that's the extension used by the ransomware. So now we got the extension. And lastly, we have a cleanup and destruction. Okay. Right. So that's the main logic of the ransomware. Next, we're gonna analyze more functions and see what are the targets of the ransomware. One of the most important functions we spot here is the get logical drive strings W, or actually it is the main function is this one. Okay, and within the function's source code, we notice a call to get logical drive strings. And here the ransomware first begins by identifying all available drives on the system. That's why it is calling the get logical drive strings. It determines the required buffer size for retrieving the logical drive strings. Okay, and then let's scroll down. We see here it runs the function again, get logical drive strings, but this time with the correct buffer size. So it runs the function again with the appropriate buffer size to collect a list of valid system drives. So it's very typical that the ransomware first enumerates the current system drives prior to the encryption process. Now, after detecting all the drives, the ransomware, let's see here, filters for fixed, local, and mounted drives. Okay, and that's why we see a call here to get drive type W. Now, after it has identified and spotted all the local drives, it begins the encryption process by encrypting the files within these drives. You can see there are calls that indicate file enumeration. So we see this call, find first file W. And also we have, let's scroll down, see if there are other calls. Let's see here. First, trying to take a look at the function calls. We have look at this one, find next file W. You see uses of this function multiple times. And also the extension is given as an argument. Now, basically, what does this do? It returns a pointer to the first occurrence of a search string in a string. So here, probably the ransomware, so this routine here probably is doing some exclusions on files encryption. We're going to have to find out what are the extensions excluded from this encryption. Okay, we scroll down and we see the statement after the encryption is done. This is sent to the terminal file locked successfully. Stage here we want to find the list of the excluded extensions from the encryption. Usually ransomwares deploy similar mechanisms to the mechanism used here to avoid encrypting files crucial to the functioning of the system. You know, because at the end, the attackers want a way out for you. So they leave the system working and they encrypt your files. They leave the system files. To find the list of the excluded extensions, we're going to have to do a bit of search here. We're going to go to search, select program text, and maybe here we can search with certain extensions. For example, the INI extensions usually used for system purposes, for the system to function. So if you can find instances of excluding this extension, we're going to find other extensions. So we select INI here and all fields, search. Okay, we have some hits here. So we see the boot INI here. Let's wait for the search to finish. Okay, now it's finished. All right, so the first file is the boot file, which is a text file usually located at the root directory, the root of the system partition. It stores the boot options for the computers. So it's logical for the ransomware to leave this file without any encryption. Let's have a look here at the first outcome. We can see references to other extensions here, such as MSI, sys, DLL, the executable functions. So probably here the ransomware only encrypts documents, pictures, videos, and leave the other extensions so that the system works correctly. Here you can see other extensions. And all these extensions are referenced on, we see here the function, this one, the function we are investigating. So that's the function used for the encryption and the exclusion of system files. And here we have to also remember that the extension used for the encryption is vanlocker. That's the extension used for the encryption. So every encrypted file will have the extension .vanlocker. Now they're saying also that ransomware encrypt network drives. So I wanted to find this by looking at the function responsible for encrypting the network drives. To do that, we're going to have to maybe again do a search. We're going to use program text, and here I selected socket. And then I'm going to do search all. So we have instances of using the socket function here. Now, this means that the ransomware uses some routine to perform encryption on any connected network drive. And also it may perform some scanning on the network to discover IP addresses and connected printers, devices. So let's have a look at these instances. Okay, let's have a look at this one. Not a socket, not a stream, not connected. Okay, another one. Socket failed. Okay, so that's correct. The ransomware tries to look for connected network drives and to perform network scanning. Now the next thing we want to do is to find out what is the function responsible for these scanning attempts. Again, we're gonna bring up the search. And now let's search for get address info. Now that's call is used to convert or to resolve any hostname into IPv4 addresses. If the ransomware uses network scanning, it's going to use this call. So let's search for this function. All fields, search all, and let's have a look. So we see, as you can see, guys, we have some hits. Let's have a look. All right, so here we have get address info used by this function. And we can see this function. Now this function init ntop is used to convert the binary IP address into its human readable dotted quad string. So after it is done retrieving local addresses, we see a couple of while loops here. This is the first one, I guess. And we have, okay, look at this one. We have this while loop. Looks like this while loop is scanning for an entire subnet because this hexadecimal value corresponds to 255, as you can see. So here probably this is an inner loop that runs through a range of numbers from 1 to 255. 1 is the starting counter, and it continues the enumeration or the iteration till it reaches the 255. So for each iteration, it constructs here you can see a candidate IP address by appending the current number to the base subnet string. And here it compares this candidate to the actual local IP address. If they match, it skips further processing. All right, so at the end, I made this diagram to summarize how this ransomware works. So first, the encryption process starts by retrieving the logical drives, as we saw earlier, using the native API calls. After retrieving the logical drives, including the names and the letters, it starts the enumeration of files and folders. And we saw that it excludes critical components represented by the extensions used by critical system files, such as the boot file, DLL files, and so on. And then after all is fine, it starts the encryption process. Now the encryption process includes files, and of course, it pivots into network encryption by encrypting the connected network drives. Uses local and hostname IP. We saw that as well. And here the ransomware generates ephemeral values to store the output of the encrypted files, temporarily, of course, and then uses this algorithm to perform the encryption. And lastly, transforms the encrypted files into hexadecimal and store them in the appropriate structure. That's in short how this ransomware works, the Vanhelsing ransomware.